Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of derivatives at points. And we're going to take a little bit of a detour, just a short detour, into rates of change and how they're related to the derivative. And then part of this conversation, actually, I'm going to glue together with a couple other application style concepts. So the first one here, we're just going to recall that the secant line is a line connecting 2 points on a curve, and the slope of that secant line is just the slope of the line connecting those 2 points. You can kind of see that formula right there, which, by the way, is like the birthplace of calculus. So everything, essentially, you've been mimicking calculus since you've been in algebra, when you've been learning slopes. Okay. Depending on the context, this formula is known as the slope. It is also known as the average velocity. It's if your function represents a position. So I should probably mention that, because a position, it's measured in distance. So, your position might be so many numbers of miles away from something, right? And then the input could be in hours, so miles per hour. So the numerator would be, the output would be in miles, the denominator would be in hours. And so position in terms of time, right? Time and position, which we'll call F. So rise over run, miles per hour. So that is definitely a velocity or a speed. Also, it is known as the average rate of change. That, even though it's a critical phrase, average rate of change, I rarely use it. I use average velocity or slope more often than not. If we allow delta x to approach 0, that's the statement right here, by allowing x2 to approach x1 or vice versa, then we get the derivative. Okay, and the instantaneous, which is the same thing as the instantaneous velocity. So when you get, basically when you allow those 2 points in the denominator to get closer together, or in other words, delta x to approach 0, you shift from looking at a slope to looking at a derivative. I should probably color code that, actually, now I'm thinking about it. So if it's a secant line, you have a slope. If it's those 2 points get dragged close together, x1 and x2, it's called a derivative. If that ratio represents the average velocity, then as you drag x1 to x2 or x2 to x1, you're talking the instantaneous velocity. And finally, if you're talking about an average rate of change in general, allowing x2 to approach x1 or vice versa, or in other words, delta x to approach 0, you're talking about the instantaneous rate of change. So there we go. It's color-coded to match up where it's discrete distances versus infinitesimally small distances between x2 and x1. All right. There's a critical language convention that we need to clarify. Velocity, oh yeah, this is very important. Velocity is a directional rate. What that means is that as you're driving your car, you're going 65 miles an hour, right? Well, if you put it in reverse and start going 10 miles an hour backwards, your velocity is -10. So you can have a negative velocity if you go backwards, or a positive velocity if you go forwards. So that's very important. Velocity can be negative. However, speed, when you're saying how fast are you going, you don't say I'm going negative so many miles per hour. You just say the absolute value. So speed is the absolute value. All right, and I kind of list out the rest there. So let's dive into instantaneous velocity, because I think that's actually one of the bigger, more important topics. Because you're likely to take physics if it's not on your plate to take physics, you should. take physics, take stats too. Anyway, if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second initially, its height in meters after t seconds is given by that function. Now we're asked to find the instantaneous velocity. Also, from now on, we're just going to call that simply the velocity after 1 second. So you throw the rock up in the air. You want to know how quickly is that rock moving at exactly 1 second. And that just requires us to find the derivative, really, of this function at 1. So again, I just want to remind you that if h is a position function and its input is time, then the limit as little h approaches 0 of capital H of a plus little h minus capital H of a over little h is the instantaneous velocity. It's a velocity, again, because if you were to graph out this function h, it is given with respect to time. Height over time. Height in meters, time in seconds. So rise over run is meters per second. That is a velocity. So there you go. That's how I know that the units for rise over run is going to represent some type of velocity. Now let's go ahead and evaluate this. And by the way, we also know, I'll write it to the right here just because it's a result of that limit, that limit is going to be h prime evaluated at a. It is the derivative function. And so let's go ahead and evaluate the derivative of that function h up above at 1 time 1 second. Okay, let's do that. I'm going to zoom in here. I'm going to say, all right, so the limit as little h approaches 0 of, notice I just gravitated toward this version of the, I say this, but this version of the derivative. It's a habit. I just do that. All right. So plugging in, we're not going to do a plus h. We're doing 1 plus h. So plugging in 1 plus h minus h at 1 all over little h. Remember, that's actually the derivative of h, big H, at 1. Or in other words, instantaneous velocity at 1. This is going to be, again, you cannot use direct substitution because, well, that just won't work right now. It causes division by 0. So this will be the limit as h approaches 0 of something over h. That something is, let's see, we're going to plug 1 plus h into the function. So it's 10 times 1 plus little h minus 1.86 times 1 plus little h squared. And we're going to subtract off that function up there evaluated at 1. All right, so I will do that. I'm going to subtract off that function evaluated at 1. Now, I want to showcase what this looks like because it's kind of nice. You're taught in mathematics constantly to simplify, right? So if I had plugged 1 in to this, I get 10 minus 1.86 because 1s don't matter there. Now, I'm not going to combine that 10 and that negative 1.86 for a very specific reason. I want to showcase this. Just bear with me while we do this. So this is going to be a big old fraction bar with an h in a denominator. Distribute that. That's 10 plus 10h minus 1.86 minus 3.72h minus 1.86 h squared. Let me just double check that, mathematics. Yep. And then minus 10 and plus 1.86. And you'll see why I didn't bother doing the arithmetic here. It's because the 10 here will cancel with the 10 there, and the negative 1.86 will cancel the positive 1.86. It's just a little trick. You don't have to do that. I just do that. Let's see, 7, 6, 2, 8. So this is going to be limit as h approaches 0 of 6.28. Let me just double check. 9. Yep. H and minus 1.86 h squared. This is all over h. You can see the h's cancel. H goes into that and takes the power off of this as well. And now I can use direct substitution. Remember, direct substitution, when you use it, you do not write the limit anymore. So you get 6.28. And now you have to discuss, what does that mean? Well, if you zoom out, we're answering the question A, which is find the instantaneous velocity of the rock at 1 second. Well, this implies that the instantaneous velocity at 1 second is 6.28 meters per second. That's not bad. So that gives us a good kind of idea of that. Now let's go ahead and answer part B. Find the velocity of the rock when t is equal to a. And actually, I should have read ahead, because if you had read that part, find the velocity of the rock at time a, you could have found that first and then plugged one in. That's very unfortunate that I did not see that, but that's okay. I'll go ahead and quickly do this. So h prime, it's a lot of copying, honestly. H prime at a is the limit as little h is approaching 0 of capital H of a plus little h minus capital H of a all over little h. And you just plug that stuff into your function. This will be the limit as little h is going to 0 of, now I'm going to plug in, let's see, I have to look at my function here. 10 times a plus h minus 1.86 times a plus h being squared, and then minus f of a, which is 10a minus, let me do it this way, minus 10a plus, is that right? That's minus 1.86 a squared, I think is what it was. I'll just double check that really quickly. Yeah, I plugged a into h, so that's 10a minus 1.86 a squared. Yeah, okay. And then denominator is h. From this point forward, I don't need to reference the function anymore. I can just kind of do the mathematics here. So this is going to equal limit as h approaches 0. There's a little bit more work when you have to take a formula and plug it in rather than just 1 and plug it in, but it's not too much more. It's 10a plus 10h minus 1.86a squared, technically. Plus 2ah, so minus 3.72ah plus h squared, so minus 1.86 h squared minus 10a and plus 1.86 a squared. And you'll see the 10a's still cancel. The negative 1.86 a squared cancels that. So the same stuff still cancels. And in fact, you still get to the same coefficient, limit as h goes to 0, of 10h minus 3.72a. Oh, no, it's ah. Those don't count. Those don't cancel at all. So it's 10h minus 3.72ah. And then, what is it? Minus 1.86 h squared all over h. Notice each of the terms in the numerator can sacrifice an h for the h downstairs. And then I can let h actually become 0 via direct substitution. If you do that, you get 10 minus 3.72a minus 0. I did that just to showcase I'm plugging in 0 for h. I just wanted to show that. This is actually equal to 10 minus 3.72a. That is actually the instantaneous velocity at time a. So if somebody said, well, what if time was 1? You'd plug in a equals, or 1 in for a, and you would get 10 minus 3.72, which is 6.28, which is what we found earlier. And finally, in this example, what will the velocity and speed of the rock be when it hits the ground? Oh, I like that question, actually. That's a pretty cool question. So we need to do two things here. This is such a good calculus question. What will the velocity of the rock be, and what will the speed of the rock be when it hits the ground? Now, obviously, you're going to say, when it hits the ground, the speed's 0. No. I mean, right before it hits the ground. Now I need to make some room on this page, so I'm going to go ahead and kill off a lot of my computation except for the h prime at a. I want to keep that. All right, I've successfully kind of moved things around. We first need to ask ourselves, when will that rock even hit the ground? So you need to solve first. So this is what I try to, again, tell all of my trig and algebra and pre-calculus students, that all your prerequisite material will come up in calculus within smaller parts of a problem, and you're just going to have to know what to do. So we are given this function for the height of the rock at any given moment. We want to know, when is that height 0? So we're going to solve 0 is equal to 10t minus 1.86 t squared. You just have to be able to interpret that. That is a prerequisite from algebra 2, honestly. And this will imply that 0 is equal to t times 10 minus 1.86 t. And therefore, we know the rock hits the ground at time 0, which is not true. Or time equals, let's see, 10 divided by 1.86, which is not a proper way to write a fraction. So I'm just going to go ahead and divide 10 by 1.86 to get roughly 5.38. I'll round to 2 decimal places. So about 5.38 seconds is when the rock will hit the ground. Let me just double check my mathematics. Factor out that t, move that over, divide. Yep. Okay. So now I know when the rock hits the ground. I just need to know what is the speed and velocity when that rock hits the ground, basically at 5.38 seconds. So I'll go back over here. Notice that I have h prime at a staring at me right there. That's going to be very useful because I want to know what's the velocity at that 5 point whatever I just said, 38, I think. So I will plug that into our velocity function, 3.72 times that 5.38. It will give me a speed or a velocity at that moment. I have my calculator, so I'm going to type in 10 minus 3.72 times the answer. And the reason why I'm stressing that it's times the answer is because this is an approximation of what my calculator is currently holding. And what my calculator is currently holding is a 5.376344086. So if I do 10 minus 3.72 times that answer, it'll be more exact. And it is very exact. It becomes negative 10 exactly. Okay. So I see that the velocity, instantaneous velocity, which I'm just going to call the velocity from this time forward, is negative 10 meters per second when the rock hits the ground. However, as we discussed earlier, that means the speed is 10 meters per second. Velocity is allowed to be negative. Speed is the absolute value of the velocity. You would never tell somebody I'm driving negative 10 miles per hour. You would say I'm going in reverse, 10 miles an hour. All right, so that's this entire problem. Now I'm including in this specific video all of the application material. So I'm going to do one more problem here, and that is about marginal cost. This ends up being a really cool concept, but it's a minor topic within a calculus course, unfortunately. So let's read the problem first. The cost of producing a single Bitcoin T years after 2011 is C. We'll just call it C, which is the cost. And it's a function of time. So C is equal to B of T. This cost considers energy usage, hardware costs, and personnel costs. So if you're going to produce Bitcoin, if you know anything about Bitcoin, it consumes a lot of energy to discover a brand new Bitcoin. So that's just how it is. So a lot of the associated price of a Bitcoin is really concerning the energy spent to produce it. So let's talk about the meaning of the derivative B prime of T. What does that mean and what are its units? And actually, I think I'm going to answer the second part first. So what are the units of B prime? Well, I need a graph to kind of help me out. So we have time in years, and this is cost, and the cost is in dollars. I don't know if it's in millions, but it's just dollars, so we'll just say dollars. Okay. So if B prime is rise over run, B prime units, B prime of t, I'll say. Let me zoom in there. The B prime of t units are rise over run, which is dollars per year. So it's a cost per year, right? Money per year. So implies cost per year to produce Bitcoins. Now, something you need to know about a derivative. A derivative is an instantaneous. So think about time here. Like here's 1 year, here's 2 years, here's 3 years, right? So if I had a curve, and I'm not going to, let's just say it looked like that. Okay. You could see a slope at this very moment is, let's just pretend -1. Okay. Does that mean that the cost is dropping by $1 for the entire year? No. It means at that very moment, at that instant, the cost to produce the next Bitcoin is dropping by $1. So I really should say it's the instantaneous cost, not just the cost per year, but the instantaneous cost per year to produce Bitcoin. Now, I should be very clear here. This is actually the cost of producing a single Bitcoin. So, it's the instantaneous cost per year to produce a Bitcoin, not Bitcoins, but to produce a single Bitcoin. And that's going to be important in our discussion. All right. So, let's see. That's actually the meaning of it too, by the way. We covered part A altogether. What does B prime of 8 equaling 4,758 mean? Well, okay, remember, time 0 is 2011, so this means in 2019, exactly like January 1st, 2019 at 12 midnight and 1 second or something like that. It's literally at time 8. This is what's weird about derivatives, is because you're at a moment in time, instantaneously at time 8, that derivative is 4,758. So I'm just going to say it means on 1/1/2019. I'll just simplify it and say it that. It means that the price of producing a Bitcoin is increasing at $4,758. So to produce the next Bitcoin, it will cost that much more. Now, this does not mean that it's actually going to cost that much more to produce the next Bitcoin, but it's at that moment predicting that it's going to cost that much more to produce the next Bitcoin. Because remember, this function represents the cost of producing a single Bitcoin. So if the moment before this, or let's say at this moment, at time 8, that B of 8, let's pretend, was equal to 1,000. That means at that time, it costs $1,000 to produce a single Bitcoin. Well, B prime of 8 being 4,758 means that over the year, that is going to jump up by $4,758 to be $5,758 to produce that Bitcoin next year. Now that's, again, over an entire year. So it's not really going to be that, but, you know, because instantaneous snapshots are just that, instantaneous snapshots. They don't really give you an average. The final question is actually the most important, in my opinion. Do you think the values of B prime of t increased or decreased in the first year of Bitcoin's release? Now, first of all, you have to remember what B prime of t means. It's the instantaneous cost per year to produce a single Bitcoin. Basically, it's the cost is the cost of producing a Bitcoin increasing or decreasing during the first year of Bitcoin's release? Now, this is a completely open-ended question. It allows for a lot of thinking in the response. So let's see, first year Bitcoin comes out. Somebody who've ever found, what is it? Nakatomi, or I forget it, the guy's name. Anyway, when it was first released, you have to think like, okay, well, did it start costing more to produce, or did the price drop? I kind of think that it would cost more and more to produce, right? Because it's based on, if you don't know, Bitcoins are based on computer algorithms and hunting down a finite set of solutions to a very complex problem, a very complex mathematical problem, actually. And the more solutions that you find, the harder it is to find future solutions. So at time 0, let's just take a look at this. It might have cost nothing to find the first few Bitcoins, to be honest with you. But as time moved on and more coins were found, the cost had to go up because it's, well, you have fewer solutions to that problem, so you have fewer Bitcoins available, so they're harder to find. But the thing about this question, it's really a very, very detailed, complex question to answer, because there's not just saying, hey, is the function increasing? That does make sense. The cost of Bitcoin rises. Okay, fine. But they're actually asking, is the cost to produce the next Bitcoin ever going to fall? And the answer to that is no. The cost to produce the next Bitcoin is always going to rise, because the more you produce, the fewer that can be found, the more it's going to cost to find. So the B prime of T is going to increase forever. That's always going to be the long-term behavior. It's going to increase. At least that's what I think. You might have a different perspective. How's that? Now this, like I said, is a very esoteric example. And I like the idea, but it's not a huge part of calculus. So it's okay if you're kind of like, oh, I don't like that one. Well, that's fine.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.